Medieval builders soaked wood in vinegar and alum, then covered it with clay. That combination resisted fire for hours. Modern treatments fail in minutes. The chemistry that made it work would surprise most fire safety engineers today. The collection of tactics, once detailed defenses against Greek fire, the terrifying incendiary weapon that could burn on water and couldn't be extinguished with conventional means. Only the title survived. But a marginal note preserved one crucial piece of information. Vinegar was used for protection against Greek fire, and the best way to protect a wall was to pour vinegar over it. This wasn't superstition. It was chemistry that Byzantine engineers understood through observation, even if they couldn't articulate the molecular mechanisms. And vinegar was just part of the formula. Medieval builders across Europe, the Middle East, and Asia discovered that combining vinegar with a crystalline salt called alum, then sealing the mixture beneath clay, created fireproofing that could save buildings, ships, and lives. The technique worked for over 2,000 years. Chinese builders used it before the Common Era. Romans copied it to protect their naval fleets. English theater owners employed it in the 1500s to fireproof stage curtains. The formula was so effective that alum remains in modern chemical fire extinguishers today, fighting oil and chemical fires where water fails. Yet somewhere between medieval guilds and modern fire codes, we lost the knowledge of why this combination worked and how to apply it correctly. We replaced empirical understanding with synthetic chemicals, gaining convenience while losing techniques that could resist flame for hours rather than minutes. The question isn't whether medieval fireproofing worked. Archaeological evidence and historical records prove it did. The question is, what exactly was this forgotten chemistry, and why did it perform so remarkably well? Alum isn't a single substance. It's a family of double sulfates, salts that combine two different metals. The most common medieval form was potassium aluminum sulfate. This technical description hides elegant simplicity. Alum is a crystalline salt that forms naturally in volcanic regions and can be extracted from certain shales through heating and chemical processing. The ancient world recognized alum's value long before understanding its structure. Egyptian records from 450 BC document construction wood treated with alum. Greeks and Romans employed it extensively, not just for fireproofing, but for dyeing textiles, tanning leather, and treating wounds. The name derives from the Latin alumen, and Pliny the Elder wrote about it in his Natural History, describing its applications across the Roman Empire. But alum's most remarkable property was its behavior when heated. Unlike most salts that simply melt or decompose, alum undergoes a complex transformation. When exposed to flame, the water molecules bound within its crystal structure, 24 of them per formula unit, evaporate rapidly. This endothermic reaction absorbs enormous amounts of heat, cooling the surrounding material. Simultaneously, the aluminum compounds left behind form a protective surface that shields underlying wood from oxygen. Medieval builders didn't know about endothermic reactions or crystal hydrates. They observed that wood treated with alum resisted ignition far longer than untreated wood. They noticed that flames touching alum-coated surfaces seemed to lose intensity. Through generations of trial and error, they refined application techniques that maximized these protective effects. The sourcing of alum became a strategic concern. For centuries, most European alum came from the Middle East, particularly from deposits near Constantinople. Alum was traded through the Mediterranean, valued more highly than many metals. Then, in 1453, Constantinople fell to the Ottoman Empire. The trade routes Europeans depended on became unreliable, and export taxes skyrocketed. This crisis drove European alum production. In the mid-15th century, a textile agent named John de Castro fled Constantinople and reached Rome, where he noticed rocks in the Tulfa Hills outside the city resembled the alum-bearing stone he'd seen in Turkey. Having worked in alum production, he recognized the potential. Soon, the Papal States controlled significant alum mines, and Pope Pius II banned imports from the East, using alum profits to fund wars against the Ottomans. The production process was extraordinarily complex. Workers extracted alunite or alum shale from quarries, then piled the rocks and roasted them for months. The heat converted aluminum silicates into soluble aluminum sulfate. Water was then used to leach the salts from the burnt rock, creating a liquor that was further processed. Potassium hydroxide, or more commonly, stale human urine, which contains ammonia and potassium compounds, was added to precipitate pure alum crystals. Yes, urine. At the peak of England's alum industry in the 18th century, producers required 200 tons of urine annually. Buckets appeared on London street corners for collection. Public toilets were built in Hull specifically to supply alum works. Ships arriving at production sites carried casks of urine alongside other cargo. This wasn't medieval ignorance. It was sophisticated chemistry using available materials. The ammonia in decomposed urine provided the exact compounds needed to crystallize pure alum from the processing liquor. Alum alone provided fire resistance, but medieval builders discovered that combining it with vinegar produced superior results. This pairing reflected understanding of how different chemicals work synergistically, even without modern theoretical frameworks. Vinegar is dilute acetic acid, typically around 5% concentration in historical preparations. When wood is soaked in vinegar, several things happen. The acid partially breaks down lignin, the polymer that gives wood its structure, allowing deeper penetration of subsequent treatments. It also alters the wood's pH, creating conditions less favorable for rapid combustion. Most importantly, acids help dissolve and carry alum deeper into wood fibers. The Roman historian Pliny documented vinegar's use in fire protection, noting that wood soaked in vinegar and then dried could resist flames longer than untreated wood. The acid treatment created a surface that charred rather than burned with open flame, a critical distinction. Charring creates an insulating layer that protects interior wood while consuming relatively little material. Open burning produces flames that spread rapidly and consume wood completely. Medieval sources describing fireproofing consistently mention vinegar as the first step. Wood was immersed in vinegar for hours or days, depending on the piece's size. After removal, the surface was allowed to partially dry before alum was applied. This sequence mattered enormously. Applying alum to wet vinegar-soaked wood allowed the salt to penetrate through capillary action. As the wood dried completely, alum crystallized within the fiber structure, not just on the surface. But vinegar wasn't the only acid medieval builders used. Salt solutions appeared in multiple recipes, and salty vinegar is mentioned specifically in Byzantine texts on Greek fire defense. Salt left on burning wood surface helps extinguish flames by interfering with combustion chemistry. When heated, salt can decompose certain organic compounds without allowing them to reach ignition temperature, effectively smothering the fire. More sophisticated medieval recipes included other fire-resistant compounds. Urine appears repeatedly. The same ammonia and phosphates that helped alum crystallization also provide fire resistance. Borax, another naturally occurring salt, was sometimes combined with alum. Sand mixed into coatings added thermal mass that absorbed heat. These weren't random ingredients, but components selected through centuries of observation about what worked. The final step in medieval fireproofing was perhaps the most important: Clay encasement. After wood had been treated with vinegar and alum, builders applied thick coatings of wet clay that dried into a hard shell. This wasn't simple mud, it was carefully selected and prepared clay with specific properties. Clay's fire resistance comes from its mineral composition. Most clays consist of aluminum silicates, the same compounds found in alum shale. When heated, clay doesn't burn. Instead, it hardens further, undergoing a process similar to pottery firing. A clay coating on wood creates a ceramic-like shield that can withstand extremely high temperatures without degrading, but clay does more than just resist heat. It excludes oxygen. Fire requires fuel, heat, and oxygen. Remove any one component and combustion stops. Clay's density prevents oxygen from reaching the underlying wood, effectively starving potential flames. Even if the outer clay surface reaches high temperatures, the wood beneath remains protected as long as the clay layer stays intact. Medieval builders understood this principle instinctively. Recipes specify clay thickness based on the level of fire protection needed. War machines that might face direct assault with flaming projectiles received multiple thick layers. Ships that needed protection but couldn't afford excessive weight used thinner applications. Building timbers in fire-prone structures got intermediate treatment. The preparation of clay mattered as much as its application. Too much sand made clay brittle. It would crack and fall away, exposing wood. Too much water created clay that shrank excessively as it dried, again causing cracks. The correct consistency, achieved through experience, created coatings that dried into solid, stable shells with minimal cracking. Some medieval formulas improved clay's properties. Adding straw or hair created fibrous reinforcement that prevented crack propagation. Mixing in lime produced clay that hardened more thoroughly. Certain recipes included crushed brick or pottery, which added thermal mass while improving the clay's adhesion to wood surfaces. The full treatment sequence: vinegar soak, alum application, clay encasement, created layered protection where each component enhanced the others. Vinegar prepared the wood and helped alum penetrate. Alum absorbed heat and released water vapor when heated. Clay excluded oxygen and provided a ceramic barrier. Together, these three simple materials could protect wood for hours in conditions that would destroy untreated timber in minutes. The fireproofing formula appeared wherever fire posed serious threats. Ships were especially vulnerable. Naval warfare increasingly involved incendiary weapons, from simple flaming arrows to sophisticated Greek fire. A single fire arrow finding untreated wood could doom an entire vessel and its crew. Roman naval architects, inheriting techniques from earlier civilizations, applied vinegar alum clay treatments to vulnerable areas of their ships. Archaeological analysis of preserved Roman vessels shows evidence of such coatings on deck timbers and around areas where cooking fires were necessary. Byzantine military manuals documented the practice for protecting war galleys against enemy fire weapons. Medieval siege warfare drove further innovations. Siege towers, mobile structures that allowed attackers to reach city walls, were primary targets for defenders' flaming projectiles. Boiling oil, burning tar, flaming arrows, all aimed at igniting these wooden towers before they could discharge their troops. Treating tower exteriors with fireproofing became standard practice. Chronicles describe siege engines covered with vinegar and alum, or protected by hides soaked in vinegar, the latter creating a double barrier of fireproof coating plus leather's natural flame resistance. The textile industry created perhaps the largest medieval demand for alum. Dyeing wool or linen required mordants, chemicals that help dyes bind to fibers. Alum was the primary mordant for bright, color-fast dyes. This economic importance drove the alum trade and ensured supply chains remained open even during conflicts. The same alum that dyed clothing could fireproof the workshops where textiles were produced. Theater construction provides documented examples from the late medieval and early modern periods. English theaters in the 1500s faced constant fire risk. Performances used open flames for lighting and special effects. Audiences packed into wooden structures with rushes or straw on floors. The combination was catastrophic waiting to happen. Theater owners responded by fireproofing stage curtains and structural timbers with the ancient formula. Historical records describe alum, ammonium, and clay mix applied to fabric curtains specifically to reduce fire risk. The practice continued into the 17th century, demonstrating the formula's proven effectiveness across centuries of use. Ordinary buildings, particularly in crowded medieval cities, benefited from fireproofing when owners could afford it. Regulations evolved, recognizing fire danger. In 1212, the mayor of London ordered stone construction and prohibited thatched roofing after fires repeatedly devastated neighborhoods. These rules acknowledged that prevention was cheaper than recovery. Where stone was impractical, chemical fireproofing offered compromise, continued use of wood construction with reduced fire risk. Given its effectiveness, why did vinegar alum clay fireproofing fade from use? The answer involves economics, chemistry advances, and changing construction methods that made old techniques obsolete, even as they remained technically sound. The Industrial Revolution transformed chemical production. Alum had been expensive to produce, requiring months-long processes and massive quantities of fuel for roasting shale. But 19th-century chemistry developed cheaper methods of manufacturing aluminum sulfate, what came to be called papermaker's alum. This industrial alum cost less, but was optimized for paper production, not fireproofing. Its formulation differed slightly from traditional alum, with impacts on fire-resistant properties that weren't immediately obvious. Simultaneously, new fire-resistant chemicals emerged. In 1735, Obadiah Wilde received the first known fire resistance patent in Britain for a mixture of alum, iron sulfate, and borax. This marked a shift from traditional formulas to deliberate chemical engineering. The 1800s brought systematic study of fire retardants. French chemist Joseph Gay-Lussac conducted famous experiments in 1821 on plant-based fabrics, establishing scientific principles for fireproofing rather than relying on empirical tradition. Asbestos appeared as a seemingly superior alternative. Known since ancient times, the Greeks called it inextinguishable. Asbestos fiber was truly fireproof rather than fire-resistant. It became wildly popular from the 1930s onward, appearing in building materials, protective clothing, and countless applications. Only decades later did its catastrophic health effects become undeniable, leading to bans in 1999 in the UK and later in other jurisdictions. Modern synthetic fire retardants promised easier application and longer-lasting protection. Intumescent paints, developed in the 20th century, expand into protective foam when heated, creating barriers between flames and underlying materials. Chemical treatments could be pressure injected into wood, making fireproofing part of the manufacturing process rather than on-site application. Construction methods changed fundamentally. Medieval buildings used large timber frames with exposed structural members. If those caught fire, the building collapsed. Modern construction often hides structural elements behind fire-rated walls and ceilings, protecting them through isolation rather than chemical treatment. Building codes mandated these approaches, making traditional fireproofing unnecessary for many applications. Most critically, the knowledge transmission system collapsed. Medieval fireproofing was craft knowledge, passed master to apprentice through demonstration and practice. How concentrated should the vinegar be? How long should wood soak? What consistency of alum solution penetrates best? These subtleties existed in craftsmen's hands, not written specifications. When construction industrialized and craft apprenticeships disappeared, the accumulated understanding vanished with them. Contemporary research into fire retardants has rediscovered why medieval formulas worked so well. The chemistry that medieval builders couldn't articulate has now been measured, tested, and explained. Aluminum compounds are still among the most effective fire retardants. Modern fire extinguishers for chemical and oil fires use dry powder containing aluminum sulfate and other aluminum-based compounds. These work through the same mechanisms medieval alum employed. Absorbing heat through endothermic decomposition, releasing water vapor that displaces oxygen, and forming surface barriers that protect underlying materials. The clay coating principle appears in modern intumescent coatings. While the chemistry differs, the fundamental concept is identical, creating an insulating barrier that prevents heat transfer and excludes oxygen. Modern versions respond more actively to heat, expanding significantly to increase thickness, but clay's passive protection through thermal mass and oxygen exclusion remains valid. Acid pretreatment, though not used in modern fireproofing, reflects sophisticated understanding of wood chemistry. Recent studies show that certain acid treatments can significantly reduce wood's flammability by altering its decomposition pathways when heated. Medieval builders stumbled upon this effect through observation, using vinegar as an available acid source. Laboratory testing of historical fireproofing recipes confirms their effectiveness. Wood treated with alum and clay can resist direct flame for 10 to 20 times longer than untreated wood. The protection isn't permanent. No historical method created truly fireproof wood, but it provided crucial extra minutes during fires, allowing intervention before total loss occurred. Heritage conservation has driven renewed interest in traditional fireproofing. Historic buildings, many using original medieval construction techniques, require period-appropriate fire protection. Modern synthetic treatments can damage or disfigure historical materials. Traditional alum clay methods provide effective protection while preserving authentic appearance and material compatibility. Some modern applications have rediscovered medieval wisdom. Natural building, movements seeking non-toxic fire protection have revived alum-based treatments. Theatrical productions sometimes use updated versions of historical formulas for fireproofing sets and curtains, particularly when synthetic chemicals might cause health concerns for performers. The medieval fireproofing formula, vinegar, alum, and clay, wasn't magic. It was empirical chemistry developed over millennia, refined through observation of what worked and what didn't. Every component had specific function. Vinegar prepared the wood and helped alum penetrate. Alum absorbed heat and released water vapor when threatened by flame. Clay excluded oxygen and created a ceramic barrier. Together, they provided protection that could mean the difference between survival and destruction. We gained efficiency when we abandoned these techniques. Modern fire retardants are easier to apply, longer lasting, more consistent in performance. These are genuine advantages that make buildings safer and construction cheaper. Industrial processes replaced craft knowledge, scaling up production in ways medieval methods never could. But we lost something too. We lost understanding that effective solutions can come from simple materials properly combined. We lost the empirical knowledge of how alum behaves under different conditions, how much vinegar penetration is enough, how thick clay must be for specific protection levels. Most significantly, we lost the cultural memory that fire protection doesn't require exotic chemicals, just careful attention to how materials interact. The Great Fire of London in 1666 is often cited as proof that medieval fire prevention failed. And it's true, the fire devastated the city. But that disaster occurred precisely because medieval practices were ignored, not because they were followed. London had prohibited thatch roofing and wooden construction centuries earlier, yet timber buildings with thatch roofs remained widespread. The fire spread through structures that should never have existed under the city's own regulations. Buildings that did use proper fireproofing survived. Stone structures, obviously. But also wooden buildings where owners had invested in alum treatment and other precautions. The fire proved not that prevention failed, but that prevention requires consistent application and maintenance. Medieval techniques worked when used correctly. The problem was economic and regulatory, not technical. Today, alum still fights fires in chemical extinguishers. The principle of oxygen-exclusion still governs fire protection. Heat absorption through endothermic reactions remains valid fire science. What changed wasn't the underlying physics. It was our willingness to invest the time, attention, and craft knowledge necessary to apply simple materials effectively. Medieval builders who soaked wood in vinegar and alum, then sealed it beneath clay, weren't primitive. They were sophisticated materials scientists working with available resources to solve pressing problems. Their solutions lasted for hours, where modern treatments fail in minutes because they understood, through generations of observation, exactly how heat, oxygen, and materials interact. That knowledge isn't lost irretrievably. The chemistry still works. The materials remain available. What we lack is the craft tradition that embedded wisdom about application, timing, and technique. We could rebuild that knowledge, testing and refining until modern practitioners match medieval expertise. Whether we choose to depends on whether we value the lessons history offers, lessons about careful attention, empirical observation, and the remarkable things simple materials can accomplish when used with skill. The medieval fireproofing trick wasn't the formula itself. It was the understanding that protection comes from patience, proper application, and respect for materials' natural properties. That's the real knowledge we forgot, and that's worth remembering, even if we never again coat wood with vinegar and alum.